So we continue our lecture series on microwave spectroscopy. We'll be talking about non-rigid rotors. All that we have been talking about so far has been based on rigid rotors, and it's based on the rigid rotor approximation, the spacing especially. But now we're going to talk about non-rigid rotors. Non-rigid rotor is like a real rotating system whose distance of rotation is not always fixed. If you recall, when we're talking about the rigid rotor approximation, we said that a rigid rotor, the distance r is always fixed. But in a real life situation, in which molecules are real, the distance of rotation is not always fixed. And there are several reasons due to this, but the most important one is the centrifugal distortion and the vibration. So what's the centrifugal distortion? The centrifugal distortion is the tendency of a molecule to stretch slightly while rotating because of our centrifugal force. And if you recall, centrifugal force is an outward force that throws body away from its center of rotation. So this is a rotating diatomic molecule. As it's rotating, the centrifugal force throws the bond length out, and it also expands the angle. So centrifugal distortion, generally what it does is that it increases the bond length, and it also stretches, opens up the bond angles, and in doing so it increases our moment of inertia, because the moment of inertia is directly proportional to the rotating distance. And once you open up the rotating distance, once you elongate the rotating distance, I is slightly increased. And because I is inversely proportional to the rotational constant P, the centrifugal distortion reduces our rotational constant. Also, it reduces, invariably, it does reduces the spacing between the spectral lines in the rotational spectrum. So the energy level for a non-rigid rotating system is given as B into J plus 1 minus dJ squared into J plus 1 squared. If you recall, the first term is the only one for a rigid rotor. However, the centrifugal distortion constant D, so B is a rotational distortion, B is a rotational constant, D is the centrifugal distortion constant. It is small, so like a small, like about 10 to minus 3 orders of B. So if we look at it, B for HCl is about 10.44. D is pretty small compared to this amount. For carbon monoxide, 1.923, that's our B. D is 0.0000061. So almost 0. So it is really small compared to B. And for HCN, it's even way smaller. So it's even though it's important, the effect is not always very same. So like I said, if you recall the rigid rotor, the transition going from a lower state to upper state have this general expression. For our non-rigid rotor, which is obtained using a similar way, the J double prime to J prime is 2B into J prime prime plus 1 minus 4D into J prime prime plus 1. So I think there's something missing here, raised to power 3, not just into J prime plus 1. So this bracket has a power exponent of 3. And if you recall, this leads to the transition at j equals to 0 is 2b. That's at 1, the molecule absorbs 4b. When j equals to, the molecule absorbs at cb, that's going from j equals to 3. And when you plot the lines, you see a spectrum where the spacing, the lines are at a spacing of 2b apart. For our non-rigid rotor, at j equals to 0, the energy level is now 2b minus 4d. So it's a little lower in energy. Now, when you go to j equals 1, it was at 4b for the rigid rotor, but even more lower in energy as a non-rigid rotor. So this is just 4d when j equals to 0, but for j equals to 1, it is now 3d. So the separation between 0 and 1, the first line, is 2b minus 28d. If you go to j equals 2, we have 6b just for the rigid rotor, but here it is 6b minus 108d. So it's even lower when compared to the j equals to 1 state, and the spacing between that line and the following line is now even smaller. But again, d is not small. We can look at this at an energy level. So 0, 1, we notice that as we go higher, the changes in energy levels are obvious. So it's not a uniform effect. However, it is more significant as j increases. So at the lower level, it can be ignored, but at a higher level, which is really important, it can no longer be ignored. So, okay, so this is that equation. So it's 2b into j prime prime plus 1 minus 4d into j prime prime plus 1 raised to power 3. Now the rotational constants can be calculated from vibration, which we'll talk about in another video. It's given as 4b cubed over v. This v is a little confusing, I know. It's a vibrational constant, and it has been expanded in this other formula. H cubed as Planck's constant, 32 pi squared I squared r squared. K is the force constant obtained from vibrational spectroscopy. So what else affects that makes the molecule non-rigid is that a molecule, even in its ground state, is in a constant state of vibration. So this is just this is phenol. This is representative of phenol, and this is just one vibration taking place. There's several vibrations that can take place. So the vibration really does cause a change in bond lengths, and hence moment on the inertia changes. Now, how does this affect this? Recall that the spacing in electronic energy level is much higher than the spacing in the vibrational energy level, and which is much higher than the spacings of the rotational energy levels. So what happens is that each electronic energy state, represented by this blue curve, has within it several vibrational energy levels. So this is one electronic state, this is another electronic state. So there are several energy vibrational levels within this electronic state. Also, within a rotational state, we have several. Within a vibrational state, we have several rotational states. Now, we said that a molecule does not rotate in its ground rotational state. Well, it's not the same for vibration. In the ground vibrational state, a molecule is in a constant state of vibration. So this may affect rotation and give rise to the the effect of non-rigid rotor. The other one, the Coriolis Effect, which is a deflection of moving objects when viewed in a rotating reference. It's the deflection part of an object in a rotating coordinate system. The object does not actually deviate from its path, but it appears to because of a coordinate reference. It is similar to the Doppler effect, which means the way the sample views the source and the way the source views the sample. However, this is really often negligible in microwave spectroscopy. It's mostly effective or used in atmospheric science. Okay, so let's work an example before we end the video. So we have 3 consecutive lines in a rotational spectrum observed at 85.544, 101.355, and 118.112 C wave numbers. So the question is, assign these values to their appropriate J to J transitions and deduce the values of B and D. So that's the rotational constants and the centrifugal distortion constants. Okay, so the frequency we know from J to J in the non-rigid approximation is given as 2b into j prime plus 1 minus 4d into j prime prime plus 1 cube. From these 3, we can obtain 3 simultaneous equations. So 855 is equal to this. We don't know what each one is. So from the last 2 equations, okay, so 855, that's 2b plus 1 to j plus 1 to j plus 1. Since this is the next line, we have as j plus 2, and this is the next line, we have j prime prime plus 3 and j prime prime plus 3. This is because we have if this is coming from, let's say, j equals to 1, so this will be coming from j equals to 2, which is j is equal to 1 plus 1. Okay, so if we, from the last 2 equations, in which case we can use anything, we're just trying to get some values out, we can subtract equation 3 from 2 from 3. So we have that 16.81 equals 2b minus 4d into j prime prime plus 2 cube minus j prime prime plus 1 cube. Recall that we said d is really small and negligible compared to b, so we can just neglect it in this equation for now and calculate an approximate value for b. So if we put the value of this b into this equation, we obtain that j equals to 85.1 minus 3, and which is approximately equal to 4. That means the transition that we see is a transition from state 4 to 5, and this is from state 5 to 6, and this from 6 to 7. So we can now calculate the accurate value for 2b by returning the equation, solving simultaneously, because we've now eliminated j, gives b equals 8.437 and d equals 435. So the other part of the equation is approximate vibrational frequency of the molecule. So we make v the subject of the formula, and we obtain 2564.4 wave numbers. So see you in the next video.